Yeah. So in this first talk, we'll explore something about dark matter, and we will learn about what are the evidences for dark matter and so on. But before I begin my talk, this has been playing for a while, so sorry we are beginning a bit late, but hopefully you could at least just stare at this graphic and kind of get mesmerized by the things orbiting, right? So this is showing, this is giving you an idea of how things orbit a central gravitational source, which is the sun in this case, and there are planets orbiting. And in that one, it is the outer planets, and in here is the inner planets. And so just keep a focus on how far the planet is and how fast it's moving. So the main message from this slide or this graphic is that as you go farther out, the planet moves slower. So the velocity decreases as you go farther from the sun. So that's the main message of this thing. You can clearly see here, right? And that graphic is 100 times slower than this one, but they have sped it up artificially. If you actually, that's why it exists in two different ones. If you actually put it in the same graphic, the outer planets will be moving 100 times slower than what it appears there. So they are really slow. The outer ones take a very long time to make one orbit, and they're going slowly. So okay, that's the visual graphic that keep in mind, and as we explore dark matter, that's the same idea we will apply to something more complicated. So how do I go to full screen here? It's maybe one of them. Control L, right? Okay. So we'll look at evidences from galaxy. That is a solar system rotation curve, and the velocity as a function of r, right? And so we will do the same thing, but now on a much larger scale, which is the galaxy scale, and we'll see that that will tell us something about dark matter. So there is an analog between the solar system and the galaxy. So then we'll tell something about the particle dark matter, what it could be, what kind of particle it could be. Then how do we find out more about it? We will realize that we have a lot of evidences for dark matter. So what can we tell more? How can we find out in experiments? What can we do? So that will be the theme of my talk. And anytime you have any questions, please feel free to stop and ask, because many other people may be having the same question. So if you ask and I have skipped something or gone too fast, then I can hopefully answer it. Okay, so before we begin, we will first take an account of what all we know right now and what all things we can account for in the universe. So the visible matter is summarized in what is called as a standard model of particle physics. This is things that we understand quite well now. Over many decades we have done many experiments and assembled a picture that everything around us, no matter what you look, in the end is made up of all of these fundamental elements that we have put down here. And that's something which is very successfully done over the last 100 years, let's say. And today we have a pretty good, complete understanding of how things are put together in terms of these particles. Is there a pointer? So you will see that, and we call this as visible matter. And I'll show you many evidences for why this is not the complete story. There are a lot of other phenomena which are not seemingly explained by these particles. But that phenomenon is what we'll focus on and see that it, thank you, it really is there out there, and how can we learn more about it. That will be the thing. So this slide summarizes everything that we know. From the next slide onwards, what we will do, like not next, but in a few slides, we'll switch over to things that we don't know, and we would like to know more about it. So the rotation curve that I showed you, that was an animation, but now we can look at a still picture of the same thing, and that's showing the various orbits, the planets rotating, revolving around the sun. And this is, you can say, is the r, the radius or the distance from the sun we'll call r, And you can also keep track of this plot. This is showing that distance from the sun as r in astronomical units. If you know what is an astronomical unit, it is just a definition where the Earth-Sun distance is defined to be 1 astronomical unit, right. So, Earth will be at 1, right, this is 1 astronomical unit. And so, if you see here, Neptune is at about 30 astronomical units. So, it is 30 times the distance, the Earth-Sun distance is where Neptune is. It is very, very far away. And this thing shows how fast it is moving. You know, it is like making an orbit. We can roughly say it is circular. So, it is revolving and it is making a circle. So, it has to travel. So, how fast is it traveling? So, this tells you the closer planets, Mercury is very close to the sun, it is moving very rapidly, it is moving very, very fast around the sun, and that is what you saw in the graphic. As you go farther out, the velocity drops, and this plot is showing you how the velocity drops. And if you know anything about functions, many of you may have studied functions, we can even extract out a functional form for this behavior. This is something that we can measure, we can look up in the sky, and since the days of Kepler, Tycho Brahe, all of those people mapped out the planets very, very precisely, and we can measure how fast they are moving. It is a bit complicated how you do it, but we have the means to do it now in physics. When you do celestial mechanics, you can do those kinds of things, and we can extract out how fast it is moving. And then you make this plot, and then the functional form of this is shown here. It goes like 1 over square root of r, right. And so, that is the main message from our observation of planets that I would like to take for continuing on with dark matter and so on. So, the main message is that it goes like 1 over square root of r. So, just keep that in mind. Now, we can explain why it should be 1 over square root of r, right. What would we use in order to do it? What equation would we use? Any guesses? If you would like to know anything about the sun and planets and all that, what equation would I pick up? Okay, Newton's equation, gravitation, right. So, we will apply the gravitational law and solve Newton's equations, and that is something we can do, and that is shown here. So, what I can say that for force balance, the centrifugal force is balanced by gravitational force. And if you remember, maybe you don't, but if you are in school and this has already happened in your grade, then centrifugal force is given by mv squared by r. Anybody remembers this? Centrifugal force mv squared by r. Okay, good, few people. And maybe it will come later in your school curriculum, but take it for the purposes here that centrifugal force is given by mv squared by r. The faster something is moving around in a circle, the more force it will be thrown outward, right. That is what centrifugal force, you might feel it on a merry-go-round or whatever, so right. If you are going around, you will feel an outward force, and that is a centrifugal force, and that is given by mv squared by r. The farther you are from the center, the lesser is the force. The more velocity that you have in the circular direction, the bigger is the centrifugal force. These are things that we commonly experience, right. And so, that you balance with the force of gravity, that is Newton's gravity equations, gravitational constant, 2 masses multiplied, the mass of the planet times the mass of the sun, capital M is the mass of the sun, divided by the distance square, right, inverse square law of gravitation. So, we put them together, we equate them, and we can solve for velocity, that is shown here, right. And you simply see that it is given by 1 over square root of r. And if you remember, oh, it is in the same graphic here, this one exactly matches this prediction. So, we can work out analytically and match with experiment, which is observation, and they perfectly agree for the solar system. That is good. That means that we know what equations are involved, we know how to do things, and we can proceed from then, right. We can say, okay, we understand gravitation, we understand planets, we know how to put together masses. So, starting from here, I can ask what else can I do, right. So, one curious thing is to see that it is working if I did not look at the sun, I only looked at the planets and asked Why are they moving around? How are they moving around? What pattern do they have? Which is this? If I never look at the sun, I can infer the presence of the sun by just looking at this observation, right? It will tell me that, oh, something is at the center, and I will make a guess that, oh, maybe it is gravity. Something is making a gravitational attraction on the planets. That is what is making them go around in a circle, right? There is that something there, and I can infer the properties of that something by looking at just the way these planets are orbiting. So I just look at the planet and how it moves, map out how long it takes, what is the orbital velocity, all of those I'll measure. And then from then on, I can guess or infer through these equations what is going on. One example I give here is from this velocity going like 1 over square root of r. From that relation, g and m don't change from planet to planet, right? G is the gravitational constant, it is a constant, and m is the mass of the sun. That also doesn't change. Every planet looks at the same sun. So this g times m is a constant. So only thing that is changing is the velocity of that planet and the radius of that planet, how far it is from the sun. So using this equation, I can just take a ratio, and very easy to see. If you know how to do this kind of algebra, you might have already seen it in school, right? So you can just do this ratio and conclude that if I take two planets, let's say I just picked randomly Earth and Jupiter, if I make this ratio, it should go like the square root, and it is inverse because it's 1 over square root of r. In this thing it is flipped, right? And I can plug in the values that are measured. People have measured how fast the planets are moving and what distance they are, right? I can just plug it in, and you can check for yourself that it is indeed true, that inverse square law gravitation and mechanics applied to this system works. And this tells me that I know what is going on. From this we conclude that there is something at the center which is exerting a gravitational influence. Without ever looking at the sun directly, I can infer that there is the sun. So that is a key point to understand before we move on to how we know that dark matter is there, right? Okay, any questions about this before I move to dark matter? Okay, good. So then let's move to dark matter, and now what we will do is we will look at much bigger scale, a galaxy scale. A galaxy is made up of 1 billion stars or 100 billion stars or something like that, right? Like our sun. We were in the neighborhood of the sun, close scale, right? But now just imagine the sky, many, many stars, and most of the stars that you see with your naked eye are all in our galaxy, right? So most of the stars that we see are in our neighborhood, which is in our galaxy. And so you have to kind of appreciate, you can appreciate how far we have to go before we start going to the scale of a galaxy. It's very, very big. The galaxy is very big. And this is showing our neighboring galaxy, which is called the Triangulum galaxy. It is also called M33. And it's a stunning picture of us looking at that galaxy. With your naked eyes, you will not be able to see it. It's very faint. But if you have a powerful enough telescope, then you can make this kind of picture. And this is showing as a function, this is r now. I'm going to apply the same law of gravitation now to this system. I look at a particular star here, and if I can somehow measure how far it is going around the center, this whole galaxy is rotating, right? Every galaxy rotates. And as it rotates, if I can actually measure the velocity with which a certain star is rotating about its center, then I can make a rotation curve, right? I can pick two stars, like for instance what I was calling Earth might be closer, and then there is a Jupiter-like thing farther out, but now these are stars, right? I can make the same rotation curve for stars. So we have developed means for measuring the velocity with which a star is moving. I will not give you details of it. Somebody is interested, you can ask me later. I can explain to you how that is done. But just take it from me that we can measure how far, by looking at Doppler shift, how fast a star is receding from us. We can make that measurement. So we can get the velocity, and we can make a measurement of how far it is from the center by just seeing how it appears to us in our telescope, right? And so we can make these two measurements, velocity and r, for every star here. And I can make a plot of distance from the center and the velocity with which it is moving around the center. And the same solar system 1 over square root of r kind of thing can be done here, except it is a little bit complicated because the mass is not all concentrated at the center like the sun is, right. The sun is a very compact object, very heavy compact object, and the planets are moving outside it. But obviously it is not like this. In a galaxy the stars are everywhere, and the star here is moving in a field of gravitation which is due to the stars inside and also outside. It's more complicated, it's a distributed mass, right. But Newton proved a theorem long ago, which says that if you pick a particular star here, its motion is determined entirely by the total mass enclosed within that circle. It doesn't see the mass outside. And so that is a thing that you can prove in classical mechanics, and just assume for now, or take it from me, that that is true. And if I pick a star here and I can compute somehow the total mass contained here, I can determine like what goes in here is now not a constant mass like the mass of the sun, but a changing mass. As I go farther and farther, the mass keeps increasing. And how does it increase? I just integrate, right? If you have studied, how many people studied integration in school already? Okay, few people, good. So if I want to take and compute the total mass contained, I just take the mass density and integrate over the radius, right. And so if you do that, I will get the total mass enclosed within that radius, and that will give me m of r, and then I plug it into this equation which we had earlier. The only difference is that the mass is changing as I now go in r. It is increasing because I will enclose more and more mass. So that simple fact now will let us predict the velocity as I move in r. If I somehow can measure how much mass is enclosed within, astronomers know how to do that, and that is got by knowing how much light is coming out of it. And then if I do that, I can determine what a velocity of the star should be. And if I actually make a measurement to ask, okay, I make a prediction and I actually do, is that what I observe? You will fail miserably. Actually what you will predict is this one. This is the 1 over root r. If I look at a star which is very far away, most of the mass is contained within. So it will really follow the same law that the solar system obeys, and so it will go like 1 over square root of r. So this large distance behavior is like 1 over square root of r. But what you observe is actually what is shown here. These are the observations. So this is telling us that applying the law of gravitation to this entire galaxy has failed miserably. Now the question is why? What has happened? Gravity we think should be valid here also, because the same gravity that's acting there and in the solar system. What happened? Very careful thought by a lot of people, lot of astronomers, starting from early hints from 1930s, and it got solidified around 1960, 1970, around that time. And people realized that what is happening here is that there is something which we call dark matter now, which is present here, and that's what is still making it rise. The mass is still, as I go outward, I am still accumulating more and more mass, which is why this velocity thing is breaking down. If you just go by what is shining, you are missing a lot of the mass. And if I put in a lot of mass outside also, right, a big thing which is not shining, then I can explain this curve. And that's what is done here. If you put in the right mass density, but in something that is dark, which we don't see, then you can show that you can actually fit the data. And that something else that we need in order to explain the rotation curve is what we call as dark matter. Right? So we can see directly from observation that it is there, but it does not shine. We are not able to record it in our telescope. We cannot see it when we look up at the sky, but it is there. And we are confident now that it is there simply because we see its effect. We see its gravitational effect, but it's not directly shining. Okay, that is the most compelling, easy to relate to evidence for dark matter. And we can even guess what extra energy density I need to put in order to match this rotation curve. And a simple exercise you can do is, if I take some dark stuff and for large radius here, if I say that there is some stuff which is going like 1 over r squared, you can almost explain this thing. And a more exact fit can actually end up explaining more precisely the rotation curve. Any questions about this? Okay. So we have now evidence from much larger scales. Now what I was showing at the galaxy scale, now each point here could be one galaxy. This is called as a Sloan Digital Sky Survey picture. It has looked at millions of galaxies, and each dot is either a star or a galaxy. Many of them are galaxies. So we have gone to such a big scale in the universe, and we can make measurement, and even here I can make measurement of the velocity with which the galaxy is receding from us and so on. If I do that measurement, I can infer the presence of dark matter even in the presence of these scales. Otherwise, you will not match the observation. I can apply the same Newton's law of gravitation to these large scale systems and infer that most of it is missing. Most of the mass that should be there, I cannot see, and that is what we mean by dark matter. I can look at even fainter things farther away, which are supernovae, and there I come into another puzzle, which I will realize there is yet another component which is not even dark matter, but it is called dark energy. Even that is needed in order to match the observation. But since this talk is on dark matter, I will not say anything more, but we also know that there is something called dark energy which we cannot explain right now. And we can go to even larger scale, and that's where we need inputs from cosmology. We have gone to such large scales that we have to really deal with the fact that the universe is expanding and then make sense of the whole picture. And this graphic tells us, as we are here, present day, and if we look farther and farther, it is looking like looking back in time, and the universe becomes hotter and hotter because the universe is expanding. And if I look backwards, in earlier it was smaller, now it has become some size, it has expanded. But if I take any gas and compress it, if I make it smaller, it heats up. So as we go back in time, the universe was hotter, and we can make guesses, we can apply our theories for early instance of the universe and ask, is it agreeing, not, what else? And we will find that when the universe becomes hotter and hotter and hotter, many phenomena I can measure, and then I will fail to explain it if I don't put in dark matter. So there also we will see that we need dark matter. And one such thing is called the cosmic microwave background. This is radiation that is left over from early times in the universe, very close to after the Big Bang. So we see radiation all around us, we can measure it, and if we want to explain these features of this microwave sky, I will find that if I don't put in dark matter, these are some of the things that are shown. If I don't put in dark matter, it will not match this nice thing that is measured, and so even there I will realize that I need to put in extra components which I don't see, and that is another evidence for dark matter. So if I go even further back in time, the universe hotter, at this time actually when this is this graphic is shown, the universe is about 10 to the 10 Kelvin, believe it or not. Right now we are at about 298 Kelvin, right? That's room temperature here on Earth. But just imagine 10 to the 10 Kelvin, that's 10 billion Kelvin, right? That's this observation, and that's called nucleosynthesis, and the amount of hydrogen, helium, lithium that we can see around us, we can actually ask, how did it get produced? And all of those elements got produced when the universe was about 10 to the 10 Kelvin. And we can understand from our physics, nuclear physics, many aspects about this also, which we have successfully done. And so that pins down how much of visible matter there is from this thing, and this tells us how much of total matter there is, and we can account for them. The difference must be dark matter, and we can very precisely account for them. And that is summarized here. So our visible part is very little. I think that is shown some part here. All of this stuff, right? The stars, hydrogen, all of that visible, tiny slice. Much of it is dark matter, more than our visible, that is this red slice. And sorry, this part is not the red slice, but this part is the dark matter. And this part is this mysterious dark energy that I told you about. So most of the stuff that we find to match observation, we don't know what it is, but we know that it is there from measurements. So that's the summary of this thing. So the dark side seems to be the dominant part in our universe. We are yet to understand what it is. Okay, I think I'm pretty much out of time, so I'll just quickly summarize these. The details are not so important. Just one thing about, if I try to explain what is dark matter, we have many guesses from particle physics, and my work also involves that kind of things. Can we try to say something more about what it is? We know it is out there, but what is it, a particle, what kind of particle, and so on, right? We can make guesses, and we have made many guesses. We are trying to see if we can detect that, if we find support for any of those ideas in experiment, and that's ongoing. And one thing I would like to say is, if we say that it is particle, new kind of particle, it must be long lived, because the universe has been around for a long time, and whatever new particle, it should not go away, right? It should be around. And it should be neutral charge, because it is not shining. If it has charge, then it will become visible, because photons will interact, it will come register in our telescope, so we should not be able to see it. And can we detect it on Earth? Many experiments are being done. So this is, for instance, a sodium iodide detector, very cold, deep in a mine, and we are trying to ask, can a dark matter particle come and hit it and leave a signature, and can we detect it? That's one such experiment that is going on. So this is another, this is a germanium detector, similar thing, very cold, deep in a mine. This is a gigantic tank of liquid xenon. It has phototubes around it, and asking, if a dark matter particle comes and interacts with any one of these, if it hits a xenon atom, it will give out some light, and can I detect that light? That kind of experiment is also going on. We are trying to look for dark matter there. This is a liquid xenon. This is called xenon 100. There are follow-ups now that have come online. This is all very interesting now, what kind of results that they may give. I'm out of time, so I'll not say anything. We are looking for antiprotons, positrons. These are satellites in space. They are sitting there and recording the energetic particles that are coming through. If there is dark matter and somehow two dark matter particles can annihilate and give you positrons or antiprotons, this satellite can detect it. It is looking for that kind of signature. And this is looking for in photons, gamma rays. If two dark matter particles gives out two gamma ray particles, and it goes and gets registered in this satellite, it is called Fermi-LAT. You can detect dark matter that way also. These are experiments that have been going on for a while now. And also in colliders, we take two protons, hit them against each other at very high energy, and new things get created. And in there, if you create dark matter, can we tell? Because it will escape unseen, right? If there is missing matter in my detector, then I can maybe guess that there might have been dark matter. So that's it. I think I went slightly over time, sorry about it, but just that's the summary, that there is dark matter. We are very sure about it now, lot of evidence for it. And then vigorous search is underway, and any time we may end up detecting it. And it's very exciting to think that maybe, there's a big component in the universe which we cannot see otherwise in some of these very clever experiments that we may end up seeing. And that detection can happen anytime. These kinds of experiments have been going on for, some few decades now, and we are becoming more and more sensitive, and maybe we'll end up detecting. So keep your like eyes open, like see, you may hear about it in the news that maybe we have detected dark matter, and that will be fantastic news. It can happen anytime. Okay, I'll stop here.